The hydrogen atom, ladies and gentlemen, is the simplest system in atomic physics. We have only one electron in the outer shell, which interacts via a proton that represents the nucleus in this system via the Coulomb force. We need a little more than Bohr's model of the atom to understand quantitatively this system. That's why we are going to use Schrödinger's wave equation today and solve the Schrödinger eigenvalue problem for the hydrogen system in position representation. But why do we need to go beyond the Bohr model? First of all, the system is not very satisfactory. The stationary orbits that prevent the atom from collapse are postulated only. There's no fundamental principle from which these stable orbits are derived. The second point is that the Bohr model has the notion of very particular orbits. However, Heisenberg's principle of uncertainty tells us that position is not a good idea because we have always an uncertainty between the position and the momentum of a particle. The basis for the quantization for discrete energy levels were discrete transitions. But there's no quantization description, so how do I arrive actually at these quantized orbits? One has to introduce so-called selection rules to account for the transition between states and to arrive at the visible or measurable transitions in hydrogen. Further on, as we shall see in future recordings, there are additional degrees of freedom, such as the internal angular momentum, the spin of a particle, and they cannot be included in Bohr's theory. And, probably the most important point, a really complex many-body problem involving more than one electron cannot be explained. So what we are going to do today is to attack this problem using the Schrödinger description of quantum mechanics. This will involve some mathematics, and we will use the position representation and Schrödinger's wave equation for that. So brace yourself with a cup of coffee and we will get started. First, we need to remind ourselves that the Coulomb problem, the hydrogen atom, is a central force problem. So we have a central force and we need to rewrite the Schrödinger equation in terms of a central, spherically symmetric potential. As a second step, we will then discuss angular momentum and angle-dependent wave functions before we arrive at studying the radial dependence of the wave function. Towards the end, I would like to give an outlook to some topics related to the structure of the hydrogen atom, which go a little bit beyond what we know today, but we will discuss already some ideas and some notions that will be discussed in the forthcoming lectures. But first, let us start with the central field. The problem is very simple. We have only one electron in the shell and only Coulomb force. We will forget for the moment about the internal structure of the nucleus and of the interaction. So we will forget about possible spins, internal degrees of freedom that you officially don't know about yet. And the extension of the nucleus will not be important. We will also assume that the nucleus has a very, very large mass, so that we can neglect any recoil or center of mass corrections. We will study the hydrogen atom without external fields, and we will use a non-relativistic treatment. Towards the end, we will make some corrections to that. So by looking at the Schrödinger equation, we know that we need to insert the Coulomb field, the Coulomb potential, to get the full Schrödinger equation. The Coulomb force just scales with 1 over r, where r is the radius, the distance between the electron and the proton. To generalize our treatment to hydrogen-like atoms, that are atoms that have more than 1 proton in the nucleus, but only 1 outer electron in the electron shell, we can write this as a function of the proton number Z, which is the electric charge of the nucleus. Our Schrödinger equation contains a Laplace operator, delta, that you can see in the slide. And this is usually the second derivative with respect to the x, y, and z positions. However, in spherical coordinates, we can rewrite x, y, and z in terms of the radius from the origin, r, and as the origin we choose the center of the proton. We have an axis to which we relate everything, and the polar angle will be referred to as the angle theta, and we have an azimuthal angle phi. So we can write x, y, and z in terms of r, theta, and phi. Doing the mathematics will lead you to the Laplace operator in these spherical coordinates. This involves some more coffee, and as a consequence, you find the equation visible on the screen. The delta operator is written as derivatives with respect to r, to theta, and to phi. You see that there are 3 terms, the first one involving derivative to r with respect to r, the second one with respect to theta, and the third one with respect to phi. I would like to point out already here that the structure of the second term, which contains the derivatives with respect to theta and phi, is actually the representation, the orbital angular momentum operator in position representation. So just by multiplying this operator with h bar, you arrive at an L squared operator. So it's the orbital angular momentum squared. If you look at this, then you find that you can rewrite the Schrödinger equation in a very simple way, involving a second derivative with respect to r for the wave function psi, involving the orbital angular momentum squared, the potential, and the total energy. How do we solve this problem? We can solve the Schrödinger equation by a separation ansatz. What does this mean? Our position-dependent wave function, psi, opening bracket, we called this in earlier presentations phi, so this is already the time dependence has been separated out already. We call it now psi, just not to mix up the wave function with the angle phi. So we can write psi of r, theta, and phi as a product of 3 different functions that each depend on r, theta, and phi only. So psi is just a product of a capital R function times a capital F a lowercase f function depending on theta, and a lowercase g function depending on phi. Inserting this ansatz into Schrödinger's equation, one of the previous transparencies, gives us the following equation. You see an equation which contains the r dependencies only on the left-hand side of the equal sign, whereas the right-hand side of the equal sign contains the angle dependence with respect to theta and phi. As these are two differential equations depending on different variables, they must be constant and they must be equal to the same constant. So we have a so-called separation constant, which we will call alpha for the moment. So the left-hand side has the R dependence only, the angle dependence on the right-hand side. We will start with the right-hand side, discussing the angle dependence. If you look again at the structure of the differential equation, I would like to point your interest to the fact that this is precisely the L squared operator that we had before. So the right-hand side and the separation constant are equivalent to an eigenvalue problem for the L squared operator. The L squared operator applied to the product function of the angle-dependent functions f and g just gives us h bar squared times alpha, where alpha is the separation constant, multiplied with the eigenfunction f times g. And that's what we're going to solve in the second step. So in a second step, we will solve the angle-dependent equation. For that, we need some more coffee, and then we will start looking at the phi and the theta dependence of these wave functions. We can, according to our separation ansatz, first of all, split the phi dependence and the theta dependence completely, and this is shown on the next transparency. Here you see that the left-hand side of the equation only depends on theta, the right-hand side depends on phi only. Again, there must be a separation constant, and we call this, because we know what comes out, minus m squared. Please note that this m is not the mass of the electron, which usually shows up in the equations. So this will be an additional quantum number, as we shall see in a minute. This separation constant minus m squared allows us to quickly write down the solution for the function g, which describes the phi dependence of the wave function. We can immediately write that g is given by an exponential with the exponent plus or minus im phi. Phi is the angle, m is our separation constant, and I is the imaginary unit. For normalization purposes, we need to divide out a 1 over square root of 2 pi. Now we are looking at a physical system where the electron picture needs to be a stationary orbit. This means that going once around in the phi angle by an angle of 2 pi must lead us to the same result. Hence, we need to require that e to the plus or minus I times 2 pi times m must be unity. This is automatically a requirement for m. And it means that m needs to be an integer quantity. So just by solving the phi dependence, we have already found from the physical boundary conditions on the wave function that that m must be an integer quantity. We have obtained a quantization in m. For solving the theta-dependent equation, we need to look even closer at the structure of the orbital angular momentum operator. We had already seen when we discussed the operator concept that the orbital angular momentum operator in position representation with respect to a particular direction z can be described by h bar over I times the angular derivative with respect to an azimuthal angle phi. So we can also find that our equation G that we have just solved, that we have just identified, is the solution of an eigenvalue problem. So the LZ operator acting on the function G just gives us an eigenvalue, which is h bar times m times G. I remind you that the eigenvalue problem for the total angular momentum squared operator we had looked at before, we know that L squared acting on F times G, which is just the sum of Lx squared plus Ly squared plus Lz squared acting on the product wave function F times G, gives us an eigenvalue h bar squared times alpha. So by subtracting the z component, we have still an xy squared plus Lx squared acting on F times G, which must be h bar squared times alpha minus m squared acting on F times G. From looking at this quantity, we find the requirement that the numbers in parentheses, alpha minus m squared, must be a positive quantity, because Lx squared plus Ly squared is a positive definite quantity physically. So we require that this term, alpha minus m squared, must be greater or equal 0. Let's look at the theta-dependent differential equation. This is shown on the next transparency, where we have now inserted the phi dependence and replaced it by m. We can substitute, in this case, a new quantity, or introduce a new quantity eta, which is just given by the cosine of theta, and thereby reformulate this theta-dependent differential equation. So the derivative with respect to the new variable eta of the product 1 minus eta squared times df over d eta plus alpha f must be 0. This equation is called Legendre's differential equation. We use it now in the following and try to solve it with a polynomial ansatz, which means we claim that we can write the function f as a polynomial in the new variable eta, which is equal to cosine theta. If f should be finite for any possible value of eta, we need to require that this series converges. This is then the case if we have a finite order of the polynomial, that is, there must be a maximum value, k max, at which the series ends, and no further terms contribute to the polynomial. From inserting our ansatz into Legendre's differential equation, we can obtain a recursion formula for the coefficients, the ak, and we can relate the ak plus 2 coefficient to the ak coefficient. As you can see, we can immediately obtain ak plus 2, and we have a factor in which contains a k times k plus 1 minus alpha in the numerator and a k plus 2 times k plus 1 in the denominator. So if this series is supposed to end at a very particular point, there must be one of these factors must be 0 at some point of time, which is obtained if the numerator vanishes. So the requirement is that k times k plus 1 minus alpha equals 0 for some value of k. Let's call this particular value k equals L. And L must be an integer number again, because k was just numbering the orders of the polynomial. Hence, we can say that for alpha equals L times L plus 1, and we chose just L as a convention for this maximum K value, with an integer value of L, gives us the separation constant that we obtained earlier. From the positive definiteness, we can derive, and I won't go into that because we would need much more coffee for that, we can arrive at some more results for the minimal and maximal values of M. We find that M, the maximal value of M, and the minimal value must be the same. We can also show, without going into details, that the maximum value of M must be the multiple, the integer multiple of the value 1/2. So it must be 1/2, 1, 3/2, 5/2, 6, and so on. But it must be a multiple, an integer multiple of 1/2. And from the L requirement above, we can also find that M, our integer value, must run from minus L to plus L. So we have 2L plus 1 values for our quantum number M given by these boundaries. What does this mean for the wave functions? We have gotten so far two quantum numbers, M and L, just from solving the differential equations. M originating from the physical boundary conditions of periodicity in phi, and L from the requirement that to solve the Legendre differential equation, the polynomial must be finite. In total, we can represent the theta-dependent function f, depending on the quantum numbers L and M, by the so-called associated Legendre functions, P, L, M, depending on cosine theta. And there's a normalization factor involving the quantum numbers L and M and functions of it and factorials of it. The associated Legendre functions can be expressed by using the regular Legendre polynomials, PL of cosine theta, and just taking the derivatives of the order M. So in total, we have the angle-dependent wave function that is given by spherical harmonic functions, which are the product functions of f and g, as we had used earlier. The angle dependence is always given as the product of the theta-dependent function f times g. This is called spherical harmonics. And you see that you can write it as a product of the associated Legendre function, PLM, and the e to the im phi function for the phi dependence. I sketched on the blackboard some very simple cases of spherical harmonics, which shows you exactly this dependence. For the simple case where L equals 0 and M equals 0, we have a spherically symmetric distribution. So this is basically a plot which tells us how the wave function is oriented with respect to theta, which is the angle with respect to the z direction, and phi, which is the angle around it. Going to the case where the L value equals 1, we have three possible M values, -1, 0, and +1. For M equals 0, the following picture emerges, which is a rotationally symmetric distribution around the z-axis. For the case L equals 1 and M equals plus or minus 1, we find a different picture, which is basically a toroid around the z-axis. This is the spherical harmonics, and these solutions occur basically for all spherically symmetric potentials. So if you, for instance, look at a three-dimensional harmonic oscillator, these functions will also describe their angle-dependent solutions. Let us have a look at the eigenvalues, which are shown on the transparency. Here we see that the eigenvalue for the total angular momentum L is given by the square root of L times L plus 1 multiplied by h bar. And for the LZ operator, which is, so to say, the projection of the total angular momentum on the z-axis, we have m times h bar. This can be visualized in a vector diagram that I have drawn on the blackboard for a particularly simple case. So we can imagine an angular momentum with a quantum number L to be drawn as a vector with a length of square root of L times L plus 1 times h bar. The orientation of this vector in various directions is possible, but only particular values of projections are allowed. They must be integer multiples of h bar again. So we have here the projection of m times h bar. We can also think about something different, namely, for instance, a vector pointing in this direction. It will have the same length, L, but it will have a different m value, namely 0 times h bar in this case. As we know, m runs from minus L to plus L, and thereby has very particular integer values that are allowed. So from solving the angle-dependent wave function, we have obtained two quantum numbers, m and L. And we now need to go to solving the radial part. We have a generic solution for all spherically symmetric problems, and we have obtained this from the L squared and the LZ operators. What we now need to do is solve the radial equation, and we use for that we have now found the value of the separation constant obtained in an earlier consideration. Our alpha is just L times L plus 1. And that's where we continue. Looking at the eigenvalue problem or the differential equation of the Schrödinger equation, we can rewrite our R-dependent function capital R by derivatives with respect to R and with the function or with the separation constant L, with L times L plus 1. We have also inserted explicitly the Coulomb force Z times E squared over 4 pi epsilon naught times R. We can solve this differential equation using an appropriate definition of variables. We introduce a new quantity kappa, which is just minus 2m over h bar squared times E, and we will look for bound states in the hydrogen atom with a total energy less than 0. So kappa will be a positive quantity. We can also introduce a new variable rho that scales the radius variable r by 2 times kappa. And we introduce a variable called beta, which includes the mass m, so this is not the quantum number, the charge z times e squared over h bar squared 4 pi epsilon naught. From these definitions, we arrive at a modified equation. I wrote here r tilde for the wave function, for the radial wave function, r tilde because it now depends on the new radius variable rho, and the two dashes indicate the second derivative with respect to the new variable rho. So we have r tilde dash dash plus 2 over rho times r tilde dash plus, you see the bracket involving beta, kappa, and rho, and L plus L times L plus 1 multiplied by by r tilde equals 0. How do we solve this equation? For that, we need some even more strong coffee. We can use for our further considerations that the wave function must taper off exponentially for large distances. We could define classical return points in the Coulomb potential, and beyond that, classically the electron could not penetrate. However, it can tunnel a little bit into this region, into this forbidden region, but the wave function must decay exponentially. So we can write our wave function r tilde as a new function s, depending on rho, times e to the minus rho divided by 2. That's just convention. So this means we arrive at a different differential equation now for the new function s. S2 prime plus 2 over rho minus 1 times s prime plus, again, a term depending on beta, kappa, and rho, and L, times S equals 0. What could the solution for this differential equation be? This is given by a power series again. So a polynomial, so to say. We take apart the rho dependence into a rho to the mu and a rho to the k, so that we can write S of rho as a sum over coefficients ak times rho to the k plus mu. Inserting this power series into the differential equation gives us some insight. By looking into very particular cases, we find that the value for mu must be given by the value of L, our quantum number for the angular momentum, for the total angular momentum. And again, we can look at various powers of rho and define a recursion formula for the coefficients and relate ak, the coefficient in the series, to ak minus 1. Again, we have a factor, this time containing k plus L minus n. And n, we have just abbreviated the ratio beta over kappa. And this numerator, again, must vanish for a particular value of k so that the polynomial is finite and we have always convergence. This requires, as L is an integer number and k is just numbering the order of the polynomial, this requires that n must be an integer as well. By looking more closely at the solution of this problem, we find that L must always be smaller or at most equal as n minus 1. By introducing the requirement, or by finding the requirement that n must be integer, we have implicitly quantized our energy, because kappa contained the energy and beta also contained the radius. So we can extract from that quantization requirements for energy or radius. By putting everything in, we can deduce an energy value which depends on the new quantum number n only. And this is shown in the transparency. And you see that En is given by z squared times e to the 4 times mc squared, and m is in this case the electron mass, over 2 h bar c squared times 4 pi epsilon naught squared times 1 over n squared. This is exactly the result that Bohr obtained within his simple model, but now we have a good reason why there are integer quantum numbers, and we have a good reason where they come from, namely from solving the Schrödinger equation. The total wave function R then depends on the quantum numbers n and L, and can be given by a normalization factor n times e to the minus kappa n multiplied by R. This was from the ansatz that brought us from the R tilde function to the S function, which we later solved, times R to the L, times a generalized Legendre polynomial, which is the solution of the preceding differential equation. And the Legendre polynomial is evaluated at the value 2 kappa n times R. The generalized Legendre polynomials relate to the regular Legendre polynomials, again by calculating the kth derivative of the Legendre function. In total, we obtained for the radial wave function various values, and I sketched some of them here on the blackboard. For very simple cases, we have the following results. I should add something to that. For the case where L equals 0 and n equals 1, we see that the radial wave function R and L tapers off very quickly. That's the solid curve in this diagram. If you square this, you get some probability as a function of the distance r in units of the Bohr radius, r a naught. You find that this is a little steeper even. If you go then to the case where L equals 0 is still valid, but you now go to the next number, the next so-called main quantum number n equals 2, so-called 2s orbital, you find a different behavior for R and L, which crosses 0 at one point, and then asymptotically also approaches 0 towards large R values. This means that the squared wave function R and L squared, the dotted line, touches 0 at a point here and then has a second node here. For values of L different from 0, we get a different distribution. So this is L equals 1 for n equals 2, a 2p orbital. And again, you see the R and L function, and now the R and L squared follows it very nicely. The probability for finding an electron at a particular distance R from the center of the nucleus, however, is not directly given by R and L squared. It is given, because of the spherical coordinates, by R squared times R and L squared. So we need to fold the dotted lines here, the dotted curves, with an R squared dependence, which pushes down the wave functions or the probabilities towards radius 0. For the 1s case, which is the L equals 0, n equals 1, we find the following behavior, and we see very nicely that the probability of finding an electron is maximal actually at the value of the Bohr radius. We have a distinct pattern which vanishes at r equals 0 because the r squared factor vanishes there, and then for the large radii it follows basically the trend here. For the 2s case, with L equals 0, n equals 2, we have two characteristic bumps, while for the 2p case, with L equals 1 and n equals 2, we have this broad distribution. I should say a few words about nomenclature. You will hear this more often in classes and in atomic physics in general. We now have three quantum numbers, n, L, and m. L and m are the solutions for the angle-dependent function, and n is important for the energy eigenvalue, for the total energy. Therefore, it is called main quantum number. The main quantum number has to be at least L plus 1. And we call n equals 1 the so-called K-shell. So all transitions of the Lyman series, for instance, in the hydrogen atom, decay to the K-shell. For n equals 2, we have the so-called L-shell. For n equals 3, the M-shell, N-shell, and so on. So this terminology is still used. The second quantum number, which is related to the total angular momentum, and L times L plus 1 square root gives us the length of this angular momentum vector. We have different values, again integer values. L equals 0 is referred to as an s orbital. So the wave functions corresponding to L equals 0 are called s orbitals. L equals 1 is called p orbital. For L equals 2, we have a d orbital, f, g, h, and so on. And I should also add that the magnetic, so-called magnetic quantum number, which is the quantum number with respect to the projection of the orbital angular momentum with respect to the z-axis, has also different values. And again, we go from minus L to plus L and find for m equals 0 a so-called sigma orbital, for m equals 1 pi, for 2 delta, and so on. Of course, for an s orbital, we have only a sigma case. For a p orbital, we have sigma and pi. Usually one writes the the configuration of an electron by a number, the main quantum number n, not KLM, but just the number, and the terminology for the L value. So a 1s orbital is just a K-shell with L equals 0. And in this case, also m is fixed. So putting everything together, we can formulate the entire wave function of the problem, of the hydrogen problem, which is a product of the radial wave function and the spherical harmonics. So in total, we can write the formula that you see on the transparency, which just contains the various factors, normalization factors for the radial part, for the angle-dependent part, and e to the minus kappa n times r to the L. We have the Legendre polynomials, and we have the Legendre polynomials, L, and we have the e to the im phi. This gives us the full wave function of hydrogen. We come now to the last part of our presentation about the hydrogen atom, and this is an outlook which takes into account some ideas that will be discussed actually during the next presentations, at least one. We have so far discussed only one electron in the shell. This is okay for hydrogen and hydrogen-like systems. However, for more complex systems, we need, of course, an expansion. We had also only considered the Coulomb force. You probably know that there is spin, and spin is something like an internal angular momentum. And with respect to that, we have magnetic properties that we will discuss in the next presentation. We will need to take that into account, and I will briefly show what is meant. We have also not included the nuclear mass. We always assume that it's very large, but in reality we have to take into account the center of mass correction. We have also assumed so far no external fields. The next to next presentation will be on external magnetic fields and external electric fields. That is also important for understanding of the system. And while for hydrogen itself a non-relativistic treatment is relatively fine, we indeed find some corrections that need to be taken into account if we want to get everything right. And for really heavy systems, we have very high velocities, so to say, on the inner radii and the inner orbits, and therefore we need to take these corrections into account. Some very sketchy remarks on further corrections that need to be taken into account. The first one is on the so-called fine structure. The fine structure is related to the magnetic properties. We find the magnetic moment to scale with the orbital angular momentum L and factor of proportionality, and we express this in some reasonable units for the atom. This is the so-called Bohr magneton mu b. In addition to that, I already mentioned, and you all know probably, that electrons do have a spin. They have a preferred direction with an internal angular momentum, which we refer to as S. Therefore, we can also introduce a magnetic moment for this spin degree of freedom, which is given by the spin vector S in units of h bar times the Bohr magneton times some proportionality factor gs. We find that there is an interaction, and we will study this in some more detail in the next presentation, between the angular motion and the spin motion. So the magnetic moment of the spin experiences, due to the rotation around the nucleus, a magnetic field. This gives rise to an interaction term, VLS, that contains the dot product of S and L. In addition, neither L nor S are really good expressions for the total angular momentum. But we have an angular momentum now which comes from the vectorial sum of the orbital angular momentum L and the spin S. We can now think about quantum numbers and introduce a new quantum number, J, which is given by the sum of the quantum numbers of spin and orbital motion, L and S. So we find indeed that J is given by L plus or minus 1/2, as the spin is just plus or minus 1/2. The spin value is 1/2 in terms of, or in multiples of h bar. So this means that the energy of our atomic system and of our hydrogen atom is expected to depend on n, the main quantum number, J, the total angular momentum, and L. Indeed, one finds if you calculate this fine structure interaction that values with L different from 0 should split according to their relative orientation of orbital angular momentum and spin. If the spin is in the opposite direction as the angular momentum, so we have a total angular momentum, say, of 1/2, if we couple 1 and minus 1/2 for the spin, we can produce two values of the total angular momentum, 1/2 and 3/2. So we get a splitting of the 2p orbital into a 2p 1/2 orbital for j equals 1/2 and into 2p 3/2. And we would expect that the 2p 1/2 is lower than the 2p 3/2. You see this in the transparency, the 2s 1/2 in this simple picture, in this simple spin-orbit interaction is unaffected. So this is just from the interaction of spin and orbital parts. I can mention in brief that there's an additional term coming in if you take into account that the nucleus, the atomic nucleus, which is circled by the electron, also has an internal degree of freedom, a nuclear spin or a nuclear total angular momentum, which can be coupled with the total angular momentum of the electron shell to a total angular momentum of the atom. This is the so-called hyperfine interaction, and we will also learn a little bit about that in the next presentation. The next point is that we need to take into account relativistic corrections. In a hydrogen atom, the typical energies of electrons are of the order of a few electron volts only. This is small compared to the rest mass of the electron of 511 keV, kiloelectron volts. However, it leads to corrections of the order of 10 to the minus 5 on the scale of the total binding energy. And this is about the same scale as we find for the fine structure corrections. So we need to take that into account. If we look closely at the relativistic corrections and on the fine structure splitting, we find that indeed we can define a total fine structure splitting as a sum of both terms, and they depend not on n only and now L, as we had argued in the case of the fine structure splitting, but on the total angular momentum only on J. So we have fine structure splitting depending on n, the main quantum number, and the total angular momentum J. The consequence is also seen in the diagram, where you see that we now find some additional terms and actually a lowering of even the n equals 1, the K shell orbit. You see that the splitting is affected for most of the orbitals, and we find again that the 2s 1/2 and the 2p 1/2 orbits now are degenerate. They are at the same energy because the energy now depends on J and not on L. However, additional corrections are even in order. And these are due to quantum electrodynamics. So far we have introduced the quantization of the motion of the electron around the nucleus in the hydrogen case. Looking more closely, we need to quantize the interaction itself. This is done in quantum electrodynamics. A way to visualize the laws of quantum electrodynamics is using so-called Feynman diagrams or Feynman graphs invented by Richard Feynman. And they show you basically what's going on. Behind these pictures is an elaborate theoretical formalism which tells you what to do. A Feynman diagram displays one random position variable and the time variable in a 2D plot. So you see visualized here the interaction of an electron with a proton. So how come they know of each other and how do they feel the Coulomb force? This is mediated in the framework of this quantum field theory by the exchange of a so-called virtual photon. This photon is not detectable outside, but it is just exchanged between the electron and the proton so that the electron can feel the attractive force of the proton. And as a consequence of this interaction, their paths, their trajectories change. However, if you look very closely, you find possible further interactions for describing this interaction. The simple Feynman diagram to the leading order for the Coulomb force tells us important things like the scaling with the fine structure constant, or that the range of the Coulomb force is basically infinite because the exchanged particle, the photon, is massless. However, there may be additional terms that play a role and may add some corrections for the Coulomb force, in particular at very small distances. So the Coulomb force looks different if you look at small distances. You can imagine the electron sending out a virtual photon and reabsorbing it later, or one more important interesting term is where the exchanged photon spontaneously breaks into an electron-positron pair due to some fluctuations. As a consequence, really the Coulomb force is reduced at very small distances. This leads to a breaking of the degeneracy of, for instance, the 2s1/2 and 2p1/2 orbits, and we achieve a splitting again, which is referred to as the Lamb shift. This was first measured by Willis Lamb in the 1940s and has been celebrated as a breakthrough of quantum electrodynamics. But that's now probably more than you always wanted to know about hydrogen anyway. So I hope I could show you some ideas of how to solve a Schrödinger equation for a three-dimensional, spherically symmetric problem. We arrived at angle-dependent functions and a radial function, and we studied them to get the orbitals of the hydrogen atom. That's all for now. Take a cup of tea and sleep well. Bye-bye.